Now, one of the interesting things about ketones and aldehydes is their ability to racemize. And we're going to look at that in this particular section, and it has to do with the fact that they can make enolates and enols. So if the alpha carbon of an aldehyde or a ketone is a chirality center, and one of the substituents on that chirality center is a hydrogen, then racemization occurs and optical activity is lost. Let's see what I mean by that. If I take a look at a ketone, this particular ketone, we see that there's a chirality center there, and we can actually figure out its absolute configuration. And when you figure out its absolute configuration, you see that it is an S stereoisomer. Now, if I take this particular stereoisomer and I know it's optically active, and I place it in a solution of acetic acid and nitric acid at room temperature or a little bit higher. So we're talking 37 degrees, it's around 100 degrees Celsius, or Fahrenheit, excuse me. So, and I let this stand for a couple of days or so. What I find is that upon returning, I have still present my S stereoisomer of the ketone, but I've also formed my R stereoisomer as well. And these happen to be in a 50-50 mixture, which we call a racemic mixture. And as we discussed in last semester, we know that racemic mixtures or 50-50 mixtures of two enantiomers are optically inactive. And so we've lost the optical activity of our stereoisomer. So what's happening here? Well, what happens is in acidic conditions or basic conditions, we already know that enols can be in equilibrium with their ketones. So here I have a ketone, it has a hydrogen on it, and therefore that hydrogen can be removed. And so in acidic conditions, I'm going to get proton transfer and then deprotonation of that hydrogen, and I'm going to form my enol. So I'm not showing that mechanism aspect of it, but because we've already talked about that, but now we go from the ketone to the enol, so that keto-enol tautomerism. Well, the enol, if I take it, if I think about the structure of that enol, it is an alkene with an alcohol coming off of it, and therefore the alkene itself is planar, and it's achiral. So the enol itself is achiral, planar achiral, and therefore when it goes back to the ketone, it can do so in one of two ways. Either the pi electrons can be protonated, so if I use a H3O plus, I can protonate the top face, right? And of course, I'm stabilizing it with the pair of electrons on oxygen, and then I'm going to deprotonate that. I'm not showing you the complete mechanism, but we see that that the hydrogen can add to the top face of the carbon, and I generate now the R enantiomer, or it can also add to the bottom face of the pi electrons, right? So the hydrogen can add to the bottom face of that alkene, and in that case, I regenerate the S enantiomer, the S stereoisomer, and therefore either one of these can happen, and so I get a racemic mixture and I lose optical activity, which is pretty cool, unless you don't want to lose optical activity.